Hey everyone, welcome back, and today let's solve Leetcode problem 1267 titled Count Servers That Communicate. A very simple but straightforward matrix problem, and I think it's a really good one to really understand for data structures and algorithms in general. So we're given a map of a server center, and then that's represented as an m by n integer matrix, where any cell that's a 1 means that there is a cell, or rather there is a server on that cell, but any cell that's a 0 means that there is no server on that cell. And we're given that two servers are said to communicate with each other if they are in the same row or two servers are in the same column. And we need to simply return the number of servers that communicate with any other server. Effectively, we're trying to find the number of servers that have other servers that are actually in their corresponding row or column. So in example 1, we have our input matrix to be a 2 by 2 input. We see 1, 0, and 0, 1. What does that tell us? Well, that tells us that we have exactly two servers. Why is that? Well, because we have exactly two cells in this input that are equal to 1. Because if you remember, any cell that's equal to 1 means it has a server on that specific cell. Now in this case, we actually have an output of 0 because no servers can actually communicate with any of the other servers. The reason why is because if we actually traverse through this grid here and check for every cell that's actually a 1, meaning it does have a server, no server has any other servers in its specific row or column, meaning that no server will communicate with any other servers, which is why we have an output of 0. They also give us an image to really show this. If we look at this server here, in its row, so horizontally, there's no other servers. In its column, there aren't any other servers as well. The only other server we have in this case would be this guy, but he is on the same diagonal, which isn't the same as a row or column. And same thing applies for this guy. If you look at the same logic, this guy isn't on the same row or column as him. They're simply just diagonally connected, and no other way either. So we have an output of 0. In example 2, we have our input matrix to be 1, 0, 1, 1. In this case, we have 3 servers, and so our output is 3 as well. Because look how all 3 of these servers are actually connected, right? All 3 of these servers have at least one other server on their specific row or corresponding column. And so since all the 3 servers can communicate, we have an output of 3 with at least one other server. Right? We don't care how many more it is, as long as it has at least one other server in its specific row or its specific column, we know that we can actually count it to be another server that can communicate with others. In example 3, we have our input matrix to be a lot larger. In this case, it's actually going to be, I believe, a 4 by 4 matrix. And in this case, we actually have 5 servers, right? One here, 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 and here. And what they actually did for us was they actually highlighted all of the servers that could communicate in blue, meaning they had at least one other server in their corresponding row or column. And this server is highlighted in red because it doesn't have any other servers in its corresponding row and column. And applying that same logic that we applied in the previous 2 examples and what's said in the problem statement as well, we see that we have 4 as output. These 2 servers can talk with each other because they're on the same column, and these 2 servers can talk with each other because they're on the same row. And so those 4 servers are communicating with some other at least one server, right? However, the server in this right bottom here, he can't communicate with any other server. Why? Because in its row, there aren't any servers, and there aren't any servers in its column as well, meaning it is kind of isolated. So for the constraints here, we see that m and n are the number of rows and columns correspondingly, and we also see that m and n are both going to be within 250, relatively pretty small inputs, right? And we're also given that the grid at any index ij is always either going to be a 0 or a 1. It's always going to actually be a valid input, either no server or server. We won't have any weird edge cases where our inputs are invalid, like having like hashtags or letters in the input, right? We won't have to actually worry about that. Okay, so now let's actually I'll give you guys a few seconds, just think of this problem in your head, and in a few seconds I'll tell you how I would optimally solve this problem in a pretty straightforward structure in a bit. Okay, so this problem, as you may or may not have seen before, depending on what level of Leetcode you're actually on, it isn't too bad of a matrix problem, right? It really is just going through all the different rows and columns in the input, counting how many servers are actually in the corresponding row and column, and checking if there are at least 2 servers in every single row and column, and counting how many servers actually have that property. That is kind of the rundown of the solution, right? But to kind of formally define what that really means, well, basically, to actually determine if a server can actually communicate, basically we need to count how many servers are actually in each row and each column of the grid, right? Keep in mind the grid is simply our input. And a server can only communicate with another server, at least one other server, if the count of the servers in either its row or its column is greater than 1, or in other words, at least equal to 2, right? Because in that case, we know we'd have at least one other server in its corresponding row or column for that server specifically to talk to, right? And if both the counts are 1, that means the server is isolated. Otherwise, that means it actually is communicating. So effectively, again, high-level rundown of the solution. Basically, we're going to use two arrays here for row and column to actually store the number of servers in each row and column of the input. And then we're going to iterate through the grid to actually populate the arrays and finally make another pass nested here in our input, basically passing through every single cell in the grid and counting servers that are not only ones, meaning they're servers, but also actually have a count that's at least 2 in their corresponding row and column, meaning checking the servers that can actually communicate, right? So with that high-level rundown out of the way, let's go ahead and dive straight into the code here. And keep in mind, we're actually going to have two different passes, one to actually build a row and column arrays, and one to actually check for the number of servers that pass the communicating criteria. So, like I talked about before, what I'm first going to do is actually initialize my row and column count. But even before that, like I usually do for matrix problems, I'm actually going to get the number of rows and the number of columns to be the length of the grid and the length of the grid at index 0. I usually do this for my matrix problems. It isn't really required, but it really just helps us iterate through the array later on, and really just makes it a little bit easier to actually access these values, right? Rows are the number of rows in the grid, and columns are the number of columns in the grid. This is a pretty quick way to do it in Python. Okay, well, now let's actually initialize the arrays or the data structures for the actual server counting for the rows and columns in the input. So I'm literally just going to call them row count and column count here. They're going to be initialized to all zeros with dimensions of the rows, and very similar logic for the column count here, all zeros. In this case, of course, it's going to have a length of the number of columns, right? Basically, very straightforward here. Row count is going to be storing the number of, or rather storing the count of these servers in each row, and the column count is going to store the number of servers in each column to actually check if the servers are actually valid in our second pass. But before we actually get to our second pass, we have to have an initial pass to actually populate these data structures, right? To actually get the number of rows, or rather the number of servers in each row and column of the input. So the way we can do that to actually explore every cell in the input, basically having nested loops for R in the range of the number of rows as our outer loop, and for C in the range of the number of columns for our inner loop here. Oops. Quick spelling error here. Right? Keep in mind this is simply to populate these two arrays, row and column count. Basically, if the current grid at RC, so if the current cell at this iteration, only if it's equal to 1, meaning only if it actually is a server, only then can we increment its specific row by 1, right? And similarly, its specific column by 1 as well. But notice how we can't just increment these arrays by 1 like that. We actually have to pass it an index. And in this case, that index is going to be the specific row and column index value, or the cell value in the current iteration. It's going to be at index R for row count, and at index C for column count, right? We're literally, for each cell, if the value is 1, meaning it's a server, we're incrementing the row count R by 1, meaning we've seen one more server, this one, in the current row, in this specific row, and also we're incrementing the row column count at C by 1, meaning we've seen one more server in its specific column at index C. Okay, well, now once this for loop is actually done executing, that means we've actually built up and populated these two arrays, and now we can actually find how many servers are actually communicating with other ones at least, right? So I'm going to initialize a count. This is our return variable. This is literally going to store the number of servers that actually communicate, and now let's actually iterate through the grid again for our second pass to see how many servers actually communicate. So for R in the range of the number of rows, again, very similar outer loop here, and for C, oops, in the range of the number of columns, simply to iterate over every single cell in the input matrix. Now, the two conditionals that we're going to have is the current cell a server and doesn't actually have another server in its specific row or column to actually communicate to, at least one other server being the key, right? So the way we can check that in Python is if grid at RC, only if it's equal to 1, and its count in its specific column or its specific row, as long as it's greater than 1, we know that we have at least one other server in that specific row or column for it to actually communicate with. So if grid.rc is equal to 1, and I'll have a parentheses this to format it a little bit better, row count, at this specific row, if that's greater than 1, meaning we have at least two servers, one besides the current one that actually is in this row, or if that's not the case, at least one column count at the specific column. If that's greater than 1, if either of these conditions are true and the current server is a 1, meaning the current cell is a server, we know we can increment our count by 1, meaning we have actually encountered another cell that actually does have a server that communicates with other ones, right? Basically, for every single server RC, we're checking if it's actually having a communication accessibility, meaning either it has another server in a specific row or column, meaning row count at that index or column count at that index is greater than 1, meaning there is at least one other server besides itself that's actually in its row or column. And if that's the case, we can increment the count by 1 because we would have seen one more cell in that iteration that actually communicates, because that's when these conditionals actually hold true. And effectively, once this for loop is actually done executing, once it actually terminates, we simply want to return the count because that would have actually stored the number of servers in the entire input that can actually communicate. That's literally our returning answer. So if I were to submit this, this would actually be accepted unless I made any syntax errors here. This would be accepted. It should be a valid solution. And as you can see, this is really just about as efficient as you can get it to be. So for a quick high-level rundown of how our solution is actually kind of working, effectively, once we actually initialize our row and column counts and the number of rows and columns, we have two different phases, right? The first phase is basically the first pass. We're calculating how many servers are actually in each row and how many servers are in each column using the row column, or rather the row count for the number of rows and columns, right? And then the second phase would actually be the second pass. We're literally looping through, again, every single cell and checking if each server has any neighbors or other servers to communicate to in a specific row or column. And if that is the case, we can increment the count by 1, meaning we've seen one more server, and we can actually return the count once that actually nested loop is done executing, right? The key here, checking if the count is greater than 1, let's go ahead and look back at the example to understand why that is. And let's just look at this example 2, right? We're in this specific row, we're in this specific column, and we're checking, well, in this case, once we're actually in the second pass, column count at this column C would have a count of 2. Since that's greater than 1, we know we have two servers in this specific column, meaning they both can communicate with at least each other. And so we can increment the count by 1 in each iteration as we actually encounter both of these cells. Right, that's basically a high-level rundown of why we actually check if the count is greater than 1, meaning we have at least two servers, one other server than the current one, to actually communicate with each other and increment our count accordingly, because that's exactly how servers communicate in this problem's constraints. So for the runtime complexity here, this is actually going to be a big O of rows times column, or m times n solution. Why? Because the first pass would be big O of m times n to actually populate the row and column count. We're iterating through each cell once, and exact same thing for the second pass, iterating through each cell once to actually check if it's a server, which is also big O of m times n. So technically it's big O of 2 times m times n if you really want to get formal here, but in reality we don't care about coefficients or constants in runtime or memory space complexities, and so simplify, the bottleneck here is really just big O of m times n. And for the memory complexity, we're actually using those two additional arrays, auxiliary memory here for the data structures, column count and row count. And that's also going to take space of the number of rows and columns respectively. And so the total memory or space complexity is going to be big O of m plus n, or rows plus columns, right? Making the solution pretty efficient, both runtime wise and memory or space time wise as well. So if you guys enjoyed the solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.